Today we're going to learn about the Heisenberg uncertainty principle. It is very normal in a high school physics class to get a question like, calculate the momentum or speed of a car at 20 meters from someplace. Or a question like, at what place will the velocity of something be 30 meters per second? And we can calculate this. Whether it's a lab or a dreadful pop quiz, we are constantly tasked with finding the position and momentum of an object. And I can say, at least for those of us who aren't failing physics, we can get these two quantities with complete certainty. Well, it turns out that when we start looking at the small world, the quantum world, which houses all the electrons, protons, and other small, sciencey things with cool names, this certainty gets thrown out the door. In 1927, German physicist Werner Heisenberg stated that we cannot simultaneously know the position and momentum of anything with complete certainty. He stated the more you know about the position of an object, the less you know about its momentum. And the more you know about its momentum, the less you know about its position. This phenomenon is explained by the equation, your uncertainty in position times your uncertainty in momentum will always be greater than or equal to some constant. The only thing to remember about this equation is really the relationship it describes. What does this equation even mean? What does this principle even mean? Well, up to now, you've probably been told that if you see someone sitting on a chair, it means that they're not moving and they're on a chair. That's not exactly true. According to Heisenberg, we don't actually know that a person on a chair is not moving with 100% certainty. They could be across the world for all we know. This sounds ridiculous, but it's true. We humans aren't affected by this uncertainty because everything on our world is big and boring. But when we start to look at things like electrons, the excitement really begins. You might be asking yourself, well, why does this principle exist? To put decades of debate and discovery together, it's because everything is both a wave and a particle. Everything. A particle is just something that occupies a location. Think of your computer that you're using to listen to my sweet voice as a particle. It's a particle because it is on your lap or desk. It is in a specific location. To be a wave, on the other hand, means that you're moving. You have momentum. And scientists can actually describe the momentum of a wave using the equation, your momentum equals some constant over your wavelength. Remember this because it's going to be important later on. That was probably hard to swallow. But think about it like this. The only reason we can't know the position and momentum simultaneously is because everything in the universe has an ongoing identity crisis. Nothing knows whether it wants to be a wave or a particle. When we embrace our wave nature, our momentum, we lose sight or information about our particle nature, our position. And when we embrace our particle characteristics, we lose information about our wave nature. This discovery that everything was a particle and a wave baffled scientists, but it was happening and scientists needed a way to describe it. Our solution? Our scientists said, let's forget about the particle and look at everything like a wave. In doing so, we today can describe the position and momentum of everything using a wave function. The wave function in itself is a whole lecture and isn't too important for our discussion, so I'm going to hold off on a lot of details. So let's say an object has this wave function. Well, I can find the momentum of the object just by using my previous equation. Momentum equals Planck's constant over wavelength. I can also describe the position by saying the wave function gives us information about the probability of where the object will be. It is almost like graphing probability versus position. What does that have to do with Heisenberg? Well, suppose a moving object has this wave function. I can actually calculate the momentum pretty easily. All I do is find the wavelength and plug it into my equation. I am pretty certain about my momentum, but let me ask you to find where the object is. That's pretty hard because it could be here and here and here. So by knowing a great deal about its momentum, I lose information about the object's position. Now let's say I put the object in a box with a length of 2 nanometers. Its wave function might look something like this. I know with great certainty that this object is in that 2 nanometer region. I know the position with great certainty. Now try to calculate its momentum. We get a problem here. I have a hard time actually finding the wavelength, so I can't really know my momentum too well. Because I've gained information about the position, I've lost information about its momentum. And that's essentially the Heisenberg uncertainty principle. Believe it or not, this principle is a governing law in quantum physics and our universe. In fact, it is the reason why things like the sun even exist and cook our beaches on a hot summer day. Thanks for watching.